This is IMO 1994, question number 4. The question asks us to determine all ordered pairs of positive integers m and n, with the quantity n to the power 3 plus 1 over m times n minus 1 being an integer. We see that the denominator contains the product of two different integers m and n, while there is only one integer, n to the power 3, in the numerator. If this fraction is an integer, it could be simplified. One simple thinking is to make use of some identities. Because the numerator contains n to the power 3. So, let's consider this one. X to the power 3 plus 1 equals to the product of x plus 1 and x squared minus x plus 1. We multiply another integer, m to the power 3, to this quantity. Now, the numerator contains m to the power 3 and n to the power 3. We expand the numerator and split it up into the sum of two fractions by means of another identity. The fraction on the left, which is pink in color, is indeed an integer. This altogether is an integer if and only if the part on the right hand side, which is m to the power 3 plus 1 over m times n minus 1, is also an integer. That is to say, m and n in the quantity could be interchanged. Let's consider the simplest case, m equals to n. The quantity could be simplified as n to the power 3 plus 1 over n squared minus 1. By means of another simple identity, we can further simplify this quantity as n plus 1 over n minus 1. We want this guy to be an integer. The only possibility is n equals to 2. M equals to n, so both of them equals to 2. And in this case, n to the power 3 plus 1 over m times n minus 1 equals to 3 is indeed an integer. So we get one solution. Let's consider further. Let n take the smallest integer, 1, and m is larger than n. This quantity becomes 2 over m minus 1. We want this guy to be an integer. There are only two possibilities, which are m equals to 2 or m equals to 3. N equals to 1. If m equals to 2, then n to the power 3 plus 1 over m times n minus 1 equals to 2 is an integer. If n equals to 1 and m equals to 3, then n to the power 3 plus 1 over m times n minus 1 equals to 1 is also an integer. So we get 3 solutions. There should be one more case we need to consider. N may not be 1. Let's say n is at least 2, while m is larger than n. This quantity may not be reducible. We want it to be reducible to become an integer. Now, one observation is this. We have m times n minus 1 in the denominator. If we can move the denominator to the numerator, we have plus 1 minus 1, so 1 is cancelled, and we have a common factor n. We put plus 1 to this quantity, and then the denominator could be moved up to the numerator. We have 1 minus 1 cancelled, and this becomes a multiple of n, which is an integer. We call this result equation 1. Now, that is to say, n to the power 3 plus 1 over m times n minus 1 equals to k times integer n minus 1. We have already assumed m is larger than n. So this quantity is less than n to the power 3 plus 1 over n squared minus 1. And this quantity on the right hand side could be further simplified as n plus 1 over n minus 1, where 1 over n minus 1 is a fraction, as we have already assumed n is not less than 2. 1 over n minus 1 is a fraction less than 1. So the only possibility is k equals to 1. So equation 1 becomes n to the power 3 plus 1 equals to the product mn minus 1 and n minus 1. Or m times n minus 1 equals to n to the power 3 plus 1 over n minus 1. Let's see whether we can express m in terms of n. It could be further simplified as n plus 1 plus 2 over n minus 1. We want this whole lot to be an integer, where 2 over n minus 1 obviously should be a fraction. This fraction becomes an integer if and only if we have n equals to 2 or n equals to 3. If n equals to 2, then m equals to 5. And the quantity n to the power 3 plus 1 over m times n minus 1 equals to 1 is an integer. If n equals to 3, then m equals to 5. And this quantity n to the power 3 plus 1 over m times n minus 1 equals to 2 is also an integer. So we obtain 2 more solutions. Now, so far we have obtained 5 different sets of solutions. However, we have already seen that m and n could be interchanged. We have already obtained the solution for n to the power 3 plus 1 over m times n minus 1 equals to an integer. So, if we interchange m and n, there should be some other sets of solutions. There are 4 of those. So, altogether, there are 9 different pairs of solutions.